In this section, we're going to talk about roots and radicals. But before we get to that, I want to talk about opposites, or mathematical opposites, operations in math that cancel each other out. And we have a few in math that do that. So, opposites. The first one that I can think about is addition. In math, we have the operation of addition. And can someone tell me what is the mathematical opposite to addition? Subtraction. If you add 2, for example, and then you subtract 2, you accomplish nothing. They cancel each other out. If you move 2 in one direction, then you move 2 steps in the opposite direction, then you end up where you were. You cancel your movements out. So addition and subtraction are mathematical opposites. They cancel each other out. There is more. I have the mathematical operation of multiplication. Can someone tell me what is the mathematical opposite to multiplication? Division. If I multiply something by 2 and then I divide it by 2, I end up where I was. Multiplication and division cancel each other out. They are mathematical opposites. Now we have something else we can do in math. We can take an exponent of something, a base. Exponents or powers. Can someone tell me what does it mean to take an exponent of something? What happens when you have an exponent? What is the definition? If you said that an exponent tells you to take the base and multiply it against itself a certain amount of times, you're absolutely correct. Whatever the exponent is, it'll always have a base attached to it, and it'll tell that base, take yourself and multiply yourself against yourself this many times. If the exponent is 2, you multiply twice the base against itself. If the exponent is 3, you multiply the base against itself 3 times. Radicals are the mathematical opposite of exponents. They do the exact opposite. If an exponent, you can think of it as a growing operation. You take a certain base and you make more of it. Radicals are the opposite. You take lots of bases and you shrink them into fewer bases. So exponents and radicals, they are opposite operation. In math, they cancel each other out. Now, this is what a radical looks like in math. It's I guess a more complex symbol than what you're used to. It's represented with this garage or house or I don't know, a lot of different terms, but this is the radical symbol. And whatever you have would go underneath. Here's the base that you're working on. Just like in exponents, radicals have bases. The base would go inside that particular house. Radicals also have something similar to exponents. They have powers. You can have exponents to various powers, both positive and negative, and they go up to infinity, both a positive and a negative infinity. You can have exponent of 1, 2, 3, 10, 100, 1,000, or you can have exponents in the negatives as well. Same thing with radicals. You can have different powers of radicals, and they are, again, if they're the opposite of exponents, they have to behave similarly. So for example, you can have a radical to the power of 2. And can you guess what the opposite of the radical of power 2 is? An exponent to the power of 2 is the opposite to a radical to the power of 2. Does that make sense? Let's take a look at some examples here. So here I have lined up some opposites. X to the first power and a radical to the first power of x are opposites. They cancel each other out. An x to the second power and a radical of x to the second power cancel each other out. Same thing with 3 and 3. Same thing with 4 and 4. Now, a mathematical conversion that I don't like at all, and I prefer that it wasn't like this, but in math, for whatever reason, they don't write the power of 2 for radicals. They just leave it blank, because power of 1 in radicals doesn't really exist. Just like an exponent to the power of 1, we don't write it, so we never write a radical to the power of 1 at all. So the smallest radical we'll ever write is the one to the power of 2. And in math, for whatever reason, I don't personally like this, but most books don't even write the 2. It's assumed that a radical without anything has a power of 2. Gets kind of confusing. I personally don't like it, but you'll see this in your math book. So if you see a radical with nothing, it's actually not 1. It's actually 2, because no one writes a radical of 1 at all. It's considered to be insignificant, so no one writes it. So if you see a radical with nothing, it's actually a radical of 2. I don't like it. I prefer writing that 2, and I'll probably keep writing it, but in most books you'll see it written with nothing, and they expect you to know that it's 2. Anyways, so when we say cancel, this is what we mean. If you were to take an exponential power that has an exponent of 2, and you were to take it under the radical that has a power of 2, the exponent of 2 and the radical of 2 would cancel each other out, leaving you with just the base with nothing, no exponent, or in this case an exponent of 1. If, on the other hand, let's say you were to take an exponential form that has a power of 4, and you were to take a radical to the 4th power, they would again cancel each other out, leaving you with just the bare base. This only works if both the exponent and the radical are of the same power. So you can't mismatch them. At least we're not going to talk about mismatches. Those do exist, and you'll talk about those in algebra, but as far as we're concerned, you only cancel if both the exponent and the radical have the same power. If that's the case, they are opposites and you can get rid of them. So here you have x to the 2nd power under the radical of 2nd power, you're left with just an x. Here you have x to the 4th power, it's taken to under the radical of 4, and it's just an x. Now, we're only going to talk about radicals to the power of 2 in pre-algebra. We're not going to mention the other radical powers. Those are going to be when you take algebra. So as far as we're concerned, we're only going to talk about radicals to the power of 2. And as I mentioned earlier, the book doesn't write this 2. It just has that. So you have to remember that if there is no power written, you assume that it's a power of 2 for the radical. Not for exponents. If there's nothing written for exponents, remember, you assume a power of 1. For radicals, if there's nothing written there, you assume a power of 2. Confusing a little bit. I apologize for that. It's one of those weird things in math. I don't know why that's the case. Now, the answer to any radical problem is called the root. So the root is the answer to a radical problem. And in the cases of radical to the 2nd power, we call the answers to these simplifications squared roots, because square represents a 2. So if you have a radical to the 2nd power problems, one of these that looks like this or just like this, then the answer is referred to it as a squared root, or a root to the 2nd power, but it's called a squared root in math. So if you're asked to find a square root, they're telling you to take the radical to the 2nd power. Again, it's just one of those terms you have to remember. So squared root is the answer to a radical of the second power. Roots are simply answers to radical problems, and squared roots are the answers to problems that have a radical to the second power, these guys here. And that's what we're going to concentrate on. We're not really going to look at anything that has a radical that's above 2. So 3, 4, 5, we're not going to look at those. You'll look at those in algebra. Next, I want to talk about perfect squares and what they are. And you don't have to copy this chart down, although it may be useful, so you're welcome to do it. The book has a similar one that you can use. Now imagine you take an integer, any integer. That means a positive or a negative number that's not a fraction or a decimal. And you multiply it against itself. 0 times 0, 1 times 1, 2 times 2, 3 times 3, 4 times 4, and so on and so on. And you can do the same thing with the negative numbers. 0 obviously doesn't have a negative. Negative 1 times negative 1, negative 2 times negative 2, negative 3 times negative 3, and so on. The result of this multiplication of two identical integers, be they positive or negative, is called a square, a perfect square. So the numbers in the middle are perfect squares. And they're created by taking an integer or an absolute value of an integer, because it doesn't really matter the distance from 0. So you can take a 5 or a negative 5, and if you multiply a 5 together, so 5 times 5, or you multiply a negative 5 together, a negative 5 times negative 5, you would get a 25. Same thing with 7, same thing with 9, and so on. Obviously this list is not inclusive. You can keep going. For example, you can have 11, which both positive and negative 11 would yield 121, 12, which is 144, 13, which is 169, and so on and so on. So this list goes on, but you need to remember the perfect squares at least up to 100, which aren't too bad. These are problems from a multiplication chart. So 9 times 9, 8 times 8, 7 times 7, and so on. So perfect squares are formed when you take an integer, positive or negative, any integer, and you multiply it against itself, you get a perfect square. And vice versa. I need you to know that a 9 can be written as 3 times 3, or as a negative 3 times negative 3. A 36 can be written as 6 times 6, or a negative 6 times a negative 6. It has to be the same number multiplied against each other. I know there are different ways of getting, let's say, 36, but I'm only interested in two identical integers being multiplied against each other. 64, you can get that either by multiplying 8 times 8, or a negative 8 times a negative 8. 100, you can get that by multiplying 10 times 10, or negative 10 times negative 10. So keep this list in mind. Now, what if I were to ask you to find the root, or the squared root of that particular radical problem? So it's a radical to the 2 problem. So in your math book, it might be written without this 2 here. It means the same thing. So it's a radical to the 2 problem, and you're asked to simplify it and to find the root of this problem, or in this case, because it's a radical to the 2, the squared root. Can someone guess as to what you can do here? How can you write 4 in exponential form? Looking at this chart here, I can write 4 as 2 to the second power, or negative 2 to the second power. They both yield a 4. 2 times 2 is 4, negative 2 times negative 2 is 4. So can I write this problem as such? I can't I? 4 is 2 to the second power, or negative 2 to the second power. So far I haven't really done anything. I just rewritten the 4 in its exponential form, one of its 2 possible exponential forms. And remember what I told you to do? When you have a radical and an exponent to the same power, what do they do to each other? They cancel each other out. Very good. So you're left with this, a 2 or a negative 2. So there are two roots or squared roots to this radical to the second power, a 2 and a negative 2. And you have to write down both answers technically because they're both correct. You can either have a 2 or a negative 2 have the solution to be the solution to this problem. But because if you take a 2 and multiply it against itself, that's a 4. If you take a negative 2 and multiply it against itself, so negative 2 times negative 2, that's also a 4. Let's take a look at another one. So I'm asking you to find the root or the squared root to this radical to the second power problem. How can you write 25 in its exponential form? If you said 5 to the second power or negative 5 to the second power, you're absolutely correct. 5 times 5 is 25. Negative 5 times negative 5 is also 25. So you could write it as such if you really wanted to. I haven't really done anything except rewritten the problem. 25 as 5 squared or negative 5 squared, or 5 to the second power and negative 5 to the second power. And once again, what happens when you have a radical and an exponent of the same power? If you said they cancel each other out, you're absolutely correct. So that would be the answer to that particular problem. Questions so far? All right, good. So let's take a look at some simple examples here. Here I have a radical problem. I have a radical to the second power, and underneath the radical to the second power I have an exponential form to the second power, m to the second power. Can you tell me what is the squared root of this particular problem? And the squared root is an answer to a radical to the second power problem. If you said it's just m, you're absolutely correct. Because once again, if you have a radical and an exponent to the second power, they simply cancel each other out. And you're left with just that base. So an m, or m to the first power, but that's still just an m. Alright, I think that was pretty simple. Let's take a look at that one. What's the answer there? Now remember when I told you in the book, for whatever reason, they simply don't write down the power of 2. So if there is no power near the radical, assume it's a 2. I know it's kind of strange. You just have to do that, and in the book every single problem does that. They don't write that 2. I don't know why. It's a very popular thing to do in math. They don't write that power of 2 for the radical. So once again, if you told me the answer is B, you're correct, because this is a radical to the second power, which cancels with an exponent of 2, leaving you with just a B. Alright, that was fairly simple. Okay, what if I asked you to find the square root of that? What would you do? What would be the square root of that? Now we haven't done these. So what you do in a problem like this, when I ask you to find a square root and they just gave you a number, is you take it under the radical to the second power, because a square root is an answer to a radical to the second power problem. So, and I'm going to write the 2 there because I like writing the 2. The book doesn't, but I like writing that 2. It makes me feel all warm and cuddly inside. And then I'm going to write the 9 right there. Now, can someone tell me, how can I write this 9 so it's an exponential form? If you remember this chart, 9 can be written in 2 ways in exponential forms. 3 to the second power, 3 times 3, or negative 3 to the second power, negative 3 times 3. So I can have it written in 2 forms, either like this, or like this. So what would be my 2 possible squared roots to this problem here? Well, on the top there, it would be just a 3, because the exponent of 2 and the radical of the second power cancel each other out. And down here, it would be negative 3. So I have 2 possible solutions. Both of these would work. Both 3 and negative 3 are valid answers. Let's take a look at another one. So the one on the bottom right. You're asked to find the square root. What's the first thing that you would do? If you said take that number underneath a root to the second power, you would be absolutely correct. Again, I'm going to write this 2 here, but the book doesn't. If there's nothing there, assume it's a 2. So I like to write it in there. The book will not. On the quiz, I'm always going to write it in, but just keep that in mind that in the book, they don't write it. Okay. So from that chart, does someone remember what are the 2 ways you can write 49 in exponential form? Seven to the second power, negative 7 to the second power. 7 times 7 is 49. Negative 7 times negative 7 is 49. So any integer, when multiplied against itself, so an identical integer, will give me the exponential form or the perfect square. So this is the perfect square form of 7 to the second power or negative 7 to the second power. So I can write it in 2 ways. Either as 7 squared or as negative 7 squared. And again, I like writing the 2's next to my radical to signify that it's power of 2. The book is not going to. So what are my 2 squared roots here? What are my 2 answers? Negative 7. I guess I didn't have to write the parentheses, but and just 7. Those are my 2 possible answers, 2 possible square roots to that particular problem. Questions so far? In math, the positive square root, because remember you can have either a negative or a positive answer to any radical problem. So here you had a positive and a negative answer. Here you had a positive and negative answer. So in math, the positive square root, so the one that I keep writing in red, is known as the principal square root or the main square root. It's not that the one is more important than the other, but in math it becomes a bit cumbersome to keep writing them both. So the convention is to write just the principal squared root unless you're asked to write both. So from this point on, whenever we work out the radical problem, we're only going to worry about the principal square root, the positive one. So we're not going to worry about the negative one. Even though it's there and it's no less important, mostly to cut down on the amount of writing we're doing and not to confuse ourselves with a bunch of negative numbers, we're only going to write the principal squared root, the positive one, unless you're specifically told to write both roots. If you're asked what are the two possible roots to this problem, then that's your cue that you need to write both. But otherwise, if you're not told anything, you only write the positive square root or the principal square root. So just a positive answer, and you don't have to write the negative. And that's the standard. If you're not told otherwise, assume you're writing the principal squared root. Now let's take a look at something that's a little bit more complex. A lot of times you'll have multiple things underneath the same radical, which really shouldn't really stress you out. And what I like to do whenever I see a problem like this, where I have, in this case, two different things underneath the radical, is to break them up and separate them. What are the two different parts here that I see underneath the radical? Well, I see a number, a 16, and then I see the variable, in this case a y term. So what I'm going to do is I'm going to break those up and I'm going to write them separately, just like this. And since they're being multiplied to begin with, I keep that multiplication. So I've broken this up, and just like with monomials, I can do this. This is not a problem. I can break things up and then recombine them and regroup them. The radical allows that. You can sort things under one radical, or you can break them up into kind of like their own little radicals. Imagine they're kind of splitting the house in two. But this makes it a little easier for us to see and work out a problem. The y one's super easy. Can someone tell me what happens when you have an exponent and a radical to the same power? They cancel each other out. So what you're left with, and I'm going to write this way back here, is just the y. So I already know that part of the answer. Now what about the number? What can I write that number, this one right here, so that it's an exponential form? What can I write it as so it's an exponential form? Now remember that chart, you had two possibilities. You had a 16 can be written as a 4 to the second power and a negative 4 to the second power. So I can have two possible ways to get that perfect square of 16. Now something else that I told you just a little bit ago is that unless you are told to specifically take both the positive and the negative, you only take the principal or the positive square root. In this problem, we weren't specified to take both roots. So you assume, if you're not told otherwise, just take the positive to keep things nice and simple. So I'm only going to use the positive, which is the 4 squared. So I'm going to write down right over here (4 to the second power), still underneath that same root. So what happens to this now? What can I do? I can cancel the radical to the second power and the exponent to the second power. They're opposites. So what am I left with? Just a 4, which now joins the y. So it's 4 times y, or simply 4y. And that's the answer to that problem. Again, I'm not going to choose the negative root. This could have been a negative 4, but because you choose the positive unless you're told otherwise, we're just going to choose the positive. It's not wrong. You could have had a negative 4y as the answer there. But it makes it cumbersome to have two different answers every single time. So in math, just for simplicity's sake, unless you're told otherwise, choose the principal root or the positive root only. But do remember that there is another possible answer here. We're just told we don't have to write it. Questions? In that case, let's take a look at this one. Very similar to the first problem. So I'm going to give you about a minute, and I want you to work this one out on your own. So I'm going to pause the video now, and I'm going to give you a minute. So work this one on your own. Okay, so the first thing that I would do is I would break this up into two separate radicals. Oh, and look, I didn't write that power of 2 here. I'm trying to show you that it's exactly the same. If there is nothing there, you consider this to be a radical to the second power. So I'm going to break this up into two different radicals. And again, I'm not going to write the powers of 2 there. I really want to, but I want to make sure that you understand that if there is nothing there, it's a power of 2. Because the book doesn't use it, and I want to make sure you aren't lost when you look at the book and go, wait, there's no number there. What radical am I talking about here? There's nothing. It's a power of 2. Next, what can I write this as? Two different things that I can write it as. A 7 squared or a negative 7 squared. But again, I'm only going to choose the positive root because unless you're told otherwise, you don't choose the negative. It's not wrong to choose it, but the convention is unless you're told, choose the negatives. Choose just the positive, so that way you don't have two different answers, and that makes things cumbersome. So I'm only going to choose the positive. And of course I have the b to the second power. What do I do next? I cancel my radical and the exponent. Now remember, even though I didn't write it, if there's nothing there, you assume that it's a radical to the second power. And as such, the exponent to the second and the radical to the second cancel each other out. And what you're left with underneath the radicals were your root answers, the 7 and the b, or in short, 7b. Questions on that one? Let's do one more, and this is the last example that we're going to do. Now this one has 3 different parts, but you solve it just like you solved the ones with 2 parts. I'm going to give you about a minute here. I'm going to pause the video, and I do want you to try this one out. Again, it looks a little different, but it's just like the ones before, except there's 3 parts now. Go ahead. Alright, so now let's see what we can do here. What are the 3 things I'm going to break this down into? Someone tell me. Right here, the 36, the W, and the M. So I'm going to write 3 separate radicals. Underneath the first one, I'm going to put 36. Underneath the second one, I'm going to put W to the second. Underneath the third one, I'm going to put M to the second. And again, these are all radicals to the power of 2. That 2 is not there, but you assume that that's a 2. Next, what do I get out of these 2? These 2 are the easy ones. The W to the second power all taken to the radical to the second, and M to the second power or all taken or all under the radical to the second. What do I get out of those 2? Well, they both cancel out their radical because power to the 2 and radical to the 2, they cancel each other out. So out of both of these, I'm going to get just a W, just an M. What about right here? How can I write 36 in exponential form? Six to the second power. Now I'm not going to take the negative possibility here. I could have, but again, you only take the positive unless you're told to take the negative as well. And again, I chose that because my chart, or if you remember this, 36 can be written as 6 to the second or negative 6 to the second, and I'm only taking the positive. So there, the outcome is just a 6. So my answer is 6 times W times M, or 6WM. Alright, that's the last problem in this lesson. Any questions so far, or any questions at all for any other parts of the lesson? Alright, thank you very much.